Look up at the sky on a clear day and you might see one aircraft, a thin white line drawn slowly across the blue. What you cannot see is everything else sharing that same sky at the same moment. Right now, as you read this, somewhere between 10 and 12,000 commercial aircraft are airborne simultaneously around the world. Each one is carrying hundreds of people through the same atmosphere, often traveling at nearly 900 kilometers per hour, often invisible to each other, often separated by distances that sound enormous on paper but shrink to almost nothing at those speeds. So why do they not collide? The answer is not luck, and it is not simply that the sky is large. It is a layered system of rules, infrastructure, and technology built over decades in direct response to disasters that made the cost of getting it wrong impossible to ignore. The early decades of commercial aviation operated on a principle that sounds almost incomprehensible by modern standards. Outside of certain controlled zones around airports, pilots were largely responsible for avoiding each other themselves. The formal term was see and avoid, which meant exactly what it sounds like. You looked out the window, you spotted other aircraft, and you steered clear of them. For a period when aircraft were slower, fewer in number, and rarely flew above the weather, the system was imperfect but survivable. On the 30th of June 1956, it stopped being survivable. A United Airlines Douglas DC-7 and a TWA Lockheed Constellation collided over the Grand Canyon while both were flying in uncontrolled airspace at the same altitude. All 128 people aboard both aircraft died. It was the deadliest aviation disaster in American history at the time, and it exposed a fundamental truth that the industry could no longer avoid. The sky needed structure, and that structure needed to be enforced rather than assumed. The collision accelerated a series of reforms that reshaped American aviation within 2 years. The Federal Aviation Administration was established in 1958 with a mandate to manage the entire national airspace as a unified system. Controlled airspace was expanded dramatically. Communication requirements were formalized. The era of pilots navigating the sky by eyesight and personal judgment was effectively over, replaced by a framework of rules, designated routes, and continuous ground-based monitoring that treated the airspace the way an engineer treats a complex system, as something that requires deliberate design to function safely. The invisible architecture that replaced the Wild West era begins with the simple concept of organized airspace. The sky is divided into layers and sectors, each one managed by specific air traffic control facilities. Aircraft flying across continents follow designated routes, not because those routes offer any physical advantage but because using common paths allows controllers on the ground to predict where aircraft will be and manage separation between them systematically. One of the foundational rules governing cruising altitude is the hemispheric rule, applied with variations across most of the world. Aircraft flying on generally eastbound headings cruise at odd-numbered altitude levels, while westbound aircraft use even-numbered levels. This single rule ensures that aircraft traveling in opposite directions along the same corridor are separated by a minimum of 300 meters vertically. Multiply this principle across 3 dimensions, apply it to thousands of aircraft simultaneously, and the result is a structured grid of invisible highways where traffic flows in organized streams rather than random directions. Managing all of this are thousands of air traffic controllers working in facilities around the world, each responsible for a specific sector of airspace. They monitor every aircraft in their sector using radar returns and transponder data, issuing instructions that maintain safe separation between flights. A transatlantic crossing might pass through the hands of a dozen different control facilities across several countries, each one handing the flight off to the next with continuous communication and overlapping surveillance coverage. The system is designed so that no aircraft is ever outside someone's awareness for long. Human attention is remarkable but finite. Controllers manage multiple aircraft simultaneously under time pressure, and the consequences of a single missed conflict can be catastrophic. This is why the final layer of the system operates entirely independently of human judgment, faster than any human could respond, and with the specific purpose of catching the situations that everything else failed to prevent. The Traffic Collision Avoidance System, known as TCAS, is a computer installed aboard commercial aircraft that monitors the surrounding airspace using signals exchanged directly between aircraft transponders. It does not depend on ground radar. It does not depend on controller awareness. It operates as a closed system between the aircraft themselves, continuously calculating the position, altitude, and trajectory of every equipped aircraft within a defined radius. When TCAS determines that two aircraft are on converging paths that will bring them within a dangerous proximity, it does not simply issue a warning. It issues coordinated instructions to both aircraft simultaneously. One crew receives a resolution advisory telling them to climb. The other receives an advisory telling them to descend. The critical design feature is that these instructions are complementary by definition. The computers communicate with each other and ensure that the responses of both crews will increase separation rather than accidentally reducing it further. The entire sequence from detection to instruction delivery happens in seconds, often resolving a conflict before the crews involved have any other indication that something was wrong, and frequently before passengers notice anything at all. The system that keeps thousands of aircraft from colliding every day is not a single invention. It is a collection of responses to failures, each one adding a layer that the previous arrangement lacked. The Grand Canyon collision added centralized authority and mandatory controlled airspace. Advancing radar technology added continuous surveillance. The hemispheric rule added geometric separation built into the routes themselves. TCAS added an autonomous safety net that operates below the threshold of human reaction time. The next time you look up and see that white line moving slowly across the sky, you are looking at one thread in a fabric that took decades of engineering, regulation, and hard-learned lessons to weave. The sky is not empty. It is one of the most carefully organized spaces human beings have ever created, and the fact that it looks effortless from the ground is exactly the measure of how well it works.